Yo, what's going on, everybody? Okay, so we left off last time with some good definition of the Hamiltonian operator, as well as kind of a general understanding of what the wave equation is. And so let's talk a little bit more in depth about the Hamiltonian operator. This, of course, corresponds to the total energy of a system. So energy of a system. And of course, this would be a quantum mechanical system, which is classical in the limit as h bar goes to 0. And this dictates basically our time evolution of the wave equation, right? Because if I took the Hamiltonian operator acting on some state psi here, if it acted on a state psi, it would give us something in terms of the time dependence, but it's imaginary, okay? And so that basically just tells us that, it gives us this quantum mechanical limit of some quantitative description of the energy levels of a system. Okay, so for a free particle, the classical energy for a free particle is going to be the energy is equal to p squared divided by 2m. Okay, and we want to make some congruency with these principles of like homogeneity and isotropy of space. And that's what led to the classical relation here. So we can derive that with classical mechanics. But we want to demand a corresponding relation now between the operators in quantum mechanics. So what we would just say here is that the energy level of a system, or the Hamiltonian, should be negative or 1 over 2m times the momentum operator p, which we defined previously as the negative I h bar times the spatial derivative of it, or nabla. Okay, and so then we could have for some Hamiltonian of a free particle that we should have some h bar squared over 2m, the negative of that, times the Laplacian. Okay, where the Laplacian is simply the nabla squared, or which would be the dot product of these two pseudo vectors. And of course they commute, okay? So, because they're pseudovectors, or that's not what pseudovectors do, but it allows us to do. We are assuming this, okay? Not necessarily true with general relativity and connections and stuff, but that's... You don't want to study general relativity and quantum mechanics at the same time. That would be very confusing. So, for a system of non-interacting particles, the Hamiltonian would be the sum of the individual Hamiltonians, as we expressed before. And so some interaction could be introduced. And so we could also rewrite the Hamiltonian, or the total energy of the system, as this Laplacian term scaled by this constant here, which would give us some kind of canonical form of the kinetic energy within quantum mechanics. But we can also have some u as well if we're dealing in 3 dimensions, x, y, z, or r, theta, phi, whatever coordinate systems you want to use. It'll look a little bit different for each form of the Schrodinger equation, just in classical mechanics, but same stuff. So the first term here, of course, we're going to call this the kinetic energy operator, okay? So this is a kinetic energy operator, and, and this is the potential energy operator, which is just the potential energy. Okay, and if we substitute this into the wave equation, if you remember the wave equation is IH bar times the time derivative acting on the quantum system. Sorry, hold on. Made a mistake. Acting on the quantum system here. It's the quantum wave function, if you will. So, okay, I want to make something really clear, is that whenever I talk about a state of a quantum system, I'm usually talking about its wave function. There's a little bit more of a connection to differential geometry, where we have a complex line bundle over the configuration space, and a section of that is the wave function. But I'm not necessarily going to get into that right now. But that is something to keep in mind when I refer to a state. I'm also referring to its wave function, and there's a lot of nuances that. Essentially, if I have the wave function of a quantum system, I have its state, and so this would be the wave equation. Okay, this is the wave equation that we talked about earlier, and so if we were to substitute that into our expression that we had earlier, we could have IH bar del psi by del t is equal to, of course, the kinetic energy operator. All right, plus u of whatever coordinates, okay? Times, and by the way, I'm outside, so if you hear birds singing and stuff, kind of cool. Yeah. So, okay, this is called the time. This together here is called the time-dependent Schrodinger equation. Okay. The time-dependent Schrodinger equation. There's a hyphen there. And so, just like we described earlier with stationary states, so a lot of times you derive the time-independent Schrodinger equation and then get the time-dependent Schrodinger equation. That is not how you're supposed to do this and how you're supposed to think about this, okay? There's a correct way to think about this. And so, if I were then to look at the degenerate case, I'm sorry, not the degenerate case. If I were to look at the stationary case where we can get the separable solutions, okay, so if I can get the wave function, the smaller psi, in terms of the coordinates, and then multiplied by this time evolution, here in terms of the energy, we can do this, and then we can solve the time-independent Schrodinger equation. Schrodinger equation. All right, so this will imply that if we look at the particular solutions only for the spatial part, this would give us the stationary spectrum. Okay? And of course, let's just keep it x, y, z, okay? Let's just keep it x, y, z for now. We're only working in 3 dimensions because that's usually you only use 3 dimensions for the Schrodinger equation at most, so everything else is going to be based off of that. But yeah, if we have this acting on that's little psi here, is equal to E on psi, we'll get our energy eigenvalues out of this, and so this is nice. And for a free particle, so sorry, this is really messy. So you can get a proper look at this. Okay, for a free particle, which basically means that u is equal to 0. So for u is equal to 0, the eigenfunctions are going to be plane waves. Okay, this would be e to the I times the momentum dotted with the position, momentum dotted with the position minus the energy. Okay, and times time, all divided by h bar. And so we're getting this phase difference, of course, and of course the energy now, we know that this is p squared over 2m in the classical sense, okay? It better make sense with the classical sense, so that I can, essentially, remember, the whole point of quantum mechanics is to get classical kind of results in the limit, all right? And so, let's clear this page here. So now what we can have here is that the spatial part, of course, for psi q was that, but also the energies, or the wavelength of those particular associated energies, okay, will be described in this form, okay, and this is what we call, sorry, this is an equal sign, this is what we call the de Broglie wavelength. Okay, this is what we call the de Broglie wavelength. Okay, that's really all you need to know. Okay, so this is kind of a very practical kind of start on the Schrodinger equation. So let's look at some properties of the Schrodinger equation. Okay, so the Schrodinger equation satisfies these things. Psi must be single valued. Okay, it must be single valued, and it must be continuous. Okay, by definition, it is a wave function, and it never goes to infinity. Okay, so it's I guess psi is psi is less than infinity. It's finite, I guess. Okay, it's never gonna be infinity anyway. Okay. Next, its derivatives. So let's just say, I guess, psi hat or psi prime. In this case, psi prime is a derivative, not another state. Okay, must also be continuous. Okay. Except, okay, so there's an exception. So there's an exception for derivatives. Exception. Surfaces where the potential becomes infinite. Okay, surfaces where the potential becomes infinite. At such a potential infinite kind of wall of the an infinite potential wall, psi goes to 0. Okay, so that's kind of what we need. So wherever let me write this out more clearly. Okay, so wherever u goes to infinity, psi is equal to 0. Okay, at those walls, whenever potentials have that, and so this will allow us to have interesting solutions for basically infinite potential wells. Okay, and we'll work out one of those. But lastly, the last condition, or the last thing that that the Schrodinger equation must satisfy, is that the energy measurements or the eigenvalues of the energies, okay, those are equivalent, must be greater than the minimum value of the potential energy. So basically just, I guess, get rid of the must be. Okay. Okay, so those are the three things that we need to do. Okay, we have all these conditions for psi, right, for the wave function to satisfy the Schrodinger equation: single valued, continuous, and finite. And then also the derivative must also be continuous, with the exception of this, and that the energy measurements or the energy eigenvalues are, of course, always above the minimum of the potential energy. Okay, and so for potential, so let's look at the special case. So special case. This is a very useful special case to investigate for the Schrodinger equation, which is whenever the potential at infinity goes to 0. So what we first need to do is describe what we could possibly measure at when potentials have this behavior, which makes physical sense, right? So the discrete spectrum is classified for energy readings that are negative. And the reason it's called discrete is because negative energy states correspond to bound states. Okay, and there's only a finite many versions of them, or many. There's only finitely many bound states. Okay, where the particle is localized. So particles are localized. Okay. The next one is the continuous spectrum. Okay. The continuous spectrum is where the energy is positive. Okay. And really what that means is that the positive energy states are unbounded, but another way to describe them is scattering. And they can take on any energy that's positive. And the reason why is because particles will travel to infinity, and so the wave function does not vanish at infinity. So the solutions exist for any positive energy readings. Okay, and so you can observe any energy reading if it's unbounded. All right, so Just means the particle has this particular property, okay? And so finite, infinite for different energy readings from the Schrodinger equation. All right. So a key departure really from classical mechanics that is that a particle here can be found in a classically forbidden region where the energy is less than the potential energy. Okay. And this is something that's true as a non-zero probability. We'll investigate this a little bit more in other chapters, but really in such a region, the classical kinetic energy would be negative, and so quantum mechanically the wave function is said to be non-zero but decays exponentially, and so there could possibly be a finite, though small, probability of finding the particle there, and this phenomenon is going to be responsible for quantum tunneling. So there's also just kind of this when we take these axioms for what they're worth, we get some of these we anticipate some of these quantum mechanical effects that are known to be kind of strange, but are properties of waves in general. Okay, so we're just kind of making these probability waves in our actual measurements. Okay, so that's kind of changing the physics a little bit. Let's look at the current density. Okay. So the classical relation for the momentum is, of course, momentum equals mass times velocity, and so this also holds for operators. So the velocity operator then must be momentum operator divided by m, which implies that we have negative IH bar over m, okay, times the nabla, okay. And what's interesting about this is the time derivative also of the probability density. This is the probability, remember this is probability density, okay, or a probability distribution, okay. This leads to a continuity equation that looks something like this, which is like a local conservation of probability. Whatever comes in must come out. And this J here, just like in E&M, it's like a current density, but this vector J, we're going to call it a probability current density. Alright, what's cool about this is we can define it as such. Okay, so it'd be IH bar over 2m, and let's just kind of make this two lines here, but it's going to be psi nabla psi star minus psi star nabla psi. And so it's going to kind of force this, it's going to kind of force these things to be equal to each other. And so if they're not equal to each other, then there's going to be a difference that we need to account for, and then take of course, the divergence of this current density to then be equal to the change in time of this probability density. Okay, so this is a local kind of, it kind of represents, so you can think about this equation here as representing the flow of probability. Okay, and with this flow of probability for a real wave function, let's say psi, okay, the current density is 0. Okay, so what we're really trying to do is get this complex kind of behavior from the self-adjointness of these operators. So let's look at, for example, for a plane wave. Let's just denote this as psi, capital Psi. Let's say we have some probability amplitude, which has some complex vector here, some complex function, eigenfunction. This complex valued eigenfunction then would dictate that the probability density must be equal to the square of the probability times that measured velocity that we have, or just probably the probability distribution squared times the velocity. So as you can see, this is kind of analogous to our clear classical interpretation of continuity. Okay. Next, what we need to do is take a look at the variational principle. So this is probably the most important thing to understand and conceptually if you get anything out of this video. All right, so the variational principle. what this means is that the energy of a ground state, so let's say E naught is the ground state. Okay, the energy of the ground state is the minimum possible value. Is the minimum possible value of the energy function, so the minimum possible value of V, okay, of E for some functional. So whenever we say this is a functional of the probability distribution itself, what we're referring to is basically this minimum value of E that we could get out of. Well, this is confusing. Let me get rid of the minimum first, okay? So this functional here, we're gonna make this equal to psi star, basically the expectation value of the energy level of the system, okay? So from as a function of our wave functions, okay? So this functional is just the expectation value of our energies, okay, or of the Hamiltonian operator, okay? And so when we do this and we get this expectation value, we can think about this here. Let's think about it like this. So if I were to put in some random trial wave function, okay, if I were to shove this into the expectation value and compute the functional, okay, the calculated energy that comes from this, okay, the calculated energy that comes from this reading will be greater than the ground state, or equal to, okay? It is greater than or equal to the ground state. So higher energy states can be found by minimizing this same functional with the additional constraint of orthogonality to all lower energy eigenfunctions. Okay? This is important because we can derive a theorem, okay? Which is that the ground state wave function, or let's just call this psi 0, okay? This ground state wave function that is associated with that ground state energy has no nodes. Okay? That's the first thing we need to understand. So there's no nodes or zeros, I guess, for finite values. Of the coordinates. Okay? There's no nodes. So this means that it has the same sign everywhere. This is because if it had nodes, one could construct a new trial function without nodes that would have a lower energy. And so this would then contradict the principle that the ground state is the minimum. Okay? And I don't know why that just erased. But it would just contradict this variational principle, okay? So what we have to do, or I guess if you were to try to exercise this, is to prove this with reductio ad absurdum, okay? Proof by contradiction, okay? So general properties of motion, really from the wave equation, can be studied, and we can get some interesting theorems from just one dimension. So let's look at that first. This is useful to understand. So if we took the spatial derivative of the we're just going to rewrite the Schrodinger equation in a different way for a particle in one dimension, okay, with some general potential, and this is all acting on psi, okay. So key theorems, okay, for a particle in one dimension. The energy levels of the discrete spectrum, okay, so wherever the energy is negative, in a 1D problem are never degenerate, okay, so non-degeneracy. For E, okay, for negative E. This just means that there can't be more than one particle taking up that energy eigenvalue, okay. It just doesn't happen in one dimension. I hope that makes intuitive sense, but the next one is oscillation. Okay. The oscillation, let's call this the oscillation theorem. this is a really simple idea. So we have eigenfunctions psi sub n, which is our basis, corresponding to the nth plus 1, the n plus 1th energy, the energy level E sub n, okay? And you can think about this with, I guess the E sub n would be the ground state, is greater than the next harmonic, going on, that discrete spectrum. This has exactly n nodes. Okay? So, okay, what this means is that if I have the ground energy, right, the ground state energy, we already kind of said that it has no nodes, right? So 0 nodes. But if we had, the next energy level would have 1 node, okay? And then, of course, the next energy level, 2 nodes, So, just in general, if you go to the next energy level, you get another node, which is pretty simple, and it's very beautiful to understand this from a one-dimensional point of view, okay? And so if we had some symmetric potential, let's say we have a symmetric potential. So let's just impose this, I guess it would equal the negative of itself here. Okay, the stationary state functions, or the stationary wave functions, let's just say for the stationary solution, we have the spatial part. This must have definite parity. And so, in other words, what this would imply, I guess, mathematically, is that they're either even here, so they have kind of that same, they have that same structure, or there also could be odd. Okay, hopefully that makes sense. So that was the oscillator, or just some principle of parity in one dimensions. So let's work a problem. Okay, let's think about the pressure on the walls of a potential box. Okay, so let's say we have energy levels for a particle in a 3D rectangular box. Okay, so let's just say we have some kind of general rectangular box with sides, I guess, A, B, and C. Okay, are the sides. And what we want to do is get the energy levels, okay, given by each of the sides. And so what we could do is say for the e to the n1, e to the n2, e to the n3, the energy levels associated with that would be associated to pi squared, h bar squared, 2m, all right, n1 squared, a squared, for n2 and n3, okay, for each of those. But the force, of course, would be the negative gradient of energy, of course. So force, of course, is equal to the negative gradient of energy. We know this in classical mechanics. And so this would be given by the negative derivative of the energy with respect to the dimension A, all right? And so we could just say that the force, we want to look at, this is actually just a basic kind of problem that I think is interesting to look at, because if we looked at a force perpendicular to the wall on the x-axis, okay, so let's just say this is the x-axis, so we'll say x is equal to A, okay, according to so this is called the Hellman, let's introduce something, the Hellman-Feynman theorem, okay? Basically, this means that if I had the expectation value of the derivative of the Hamiltonian it is the derivative of the energy eigenvalue. So let's look at this. So if we have the force, that basically just means if I were to take the expectation value of the derivative of the Hamiltonian in general, okay, with respect to the coordinate, what would happen is that I would get the negative derivative of the energy eigenvalue. Okay? This is a pretty interesting thing to try to understand. Okay? So we just, of course, we have some quantum particle confined to this rectangle. We just want the x component of the pressure. Okay? That's all we're trying to do. And so, and this is the force per unit area. Okay? So what we're going to do here is differentiate the energy expression with respect to A. All right? So we're just going to differentiate this with respect to A, and I think this is a good exercise to try doing, because really we can just look at the component in the x here. So we're going to want to, of course, differentiate psi or pi squared, and the reason I didn't write out the rest of these terms is because, of course, they do not matter when I differentiate, okay? So this would be equal to then the negative, right? So give us the negative of pi squared h bar squared in 1, 2 times m e2m divided by 2m negative 2. Of course, with the product rule of differentiation, and this would then get give us pi squared h bar squared in 1 squared divided by m a cubed. And so the pressure then on the wall, of course, is just divided by the area of the wall, of course. So that would then give us, so the pressure would be equal to Fx. And so the area of the wall, in this case, since we're in the x direction, we're only interested in, I guess, this side here, which would then, you know, we could then just divide the whole thing by this, and so we would just plug this in to there, okay? And so this is really interesting because we can get, we can say that the expectation, and this is derived somewhere online, you can find it, but really this is a nice result that you can just kind of take for granted. If you have the expectation value of the Hamiltonian with respect to the variation of some of this coordinate, the negative of that gives you the force, and so of course this would then correspond to taking the derivative of the energy eigenvalues. So that's very helpful. I think that's something that's worth mentioning. Okay, so let's just write out for argument's sake, so we get a complete answer. Pi squared h bar squared in 1 squared divided by ma cubed. Okay, ma cubed, and this a cubed is coming from the derivative of that energy term in that on that direction here. Okay, or on that area. All right. And it should be a symmetrical argument, okay? So the pressure exerted, so this basically tells you the pressure exerted by a particle in a specific quantum state, okay? In a specific quantum state in 1, in 2, and in 3. So really it only, in this case, would depend on in 1 for the in 1 component of that energy eigenvalue on this particular area. You see what I'm saying? And it would be the same kind of process for each of these areas as well. So hopefully that's useful. I think that's a great problem to kind of think about. So let's talk about the linear oscillator. Okay. So for a simple harmonic oscillator in classical mechanics, let's see what happens to it in quantum mechanics. So if we had some some 1/2 m omega squared with frequency with respect to the coordinate. Sorry, not x to x. Okay, it's just the square of the coordinate. That's its potential, and so this would give us, of course, the Schrodinger equation, which would be should look like the negative of h bar. You know, scaling this one-dimensional kind of Schrodinger equation here, and then 1/2 mw squared or omega squared. X squared, okay, times psi is equal to the energy eigenvalues because we're in a stationary state, okay? Since u is going to infinity, as the magnitude of x goes to infinity, I want you to think about that. So if I were to just pull like the spring or whatever oscillatory system that helps you imagine simple harmonic motion the best, which is most likely just a spring system with Hooke's law. Really, the motion will always be finite. Okay, it's always going to be finite, and so the energy, we can conclude that the energy spectrum is entirely discrete, where the energy spectrum is always going to be negative. And so the energy levels are found to be equally spaced too. And so when you go through this, you can say that the energy eigenvalues here are going to be in. I'm not going to go through exactly how to derive this, but this is something that I think is interesting for you to research on yourself. But the energy eigenvalues are going to be equally spaced by the integers. Okay. All right. And it's going to satisfy it for all the integers. And so a key result from this, from looking at the energy or at the energy eigenvalues for some kind of simple harmonic oscillator system, is that, guess what? The ground state energy, okay? So the ground state energy, 1/2 h bar omega, is known as the 0-point energy. Oh, sorry. This is a non-zero ground state energy. Okay, so the lowest energy that this simple harmonic oscillator could be is non-zero, which is kind of weird to think about. This is known as the 0-point energy. Okay, what is a 0-point energy? Well, it's actually, if you think about this, okay. If you think about this, this is a direct consequence, since there's an h bar there, of the uncertainty principle. And so this is why the uncertainty principle is fundamental to quantum mechanical systems. Okay, to our attempt to solve the wave equation for a simple harmonic oscillator. This gives us something completely different from classical mechanics, okay? And so if the particle were at rest, so if E is equal to 0, or particle is at rest, what does that mean? And if it's at some bottom of the well, okay, where x equals 0, okay, assume that, both its position and momentum would be precisely known, which is forbidden. So we would know delta 0 or delta P and delta T would be known. This is probably the weirdest thing so far to think about. For a particle at rest, for any particle at rest, momentum and position should be known in general, right? But this is forbidden. Like I'm gonna get a color, okay? Okay, this is forbidden, okay? So what do we do? We need to describe wave functions, and the solutions for this. The solution for these new eigenvectors, eigenfunctions, would take on this new form, and we have to kind of make this compatible with the fact that the 0-point energy, there's an inherent uncertainty principle that's associated with having a particle at rest, right, or having a particle that reads with 0 energy. Okay, you don't want to trash it yet. Okay. So what's going to happen here is we're going to get wave functions, or psi sub n. When we solve this, we're going to be given polynomials that are of the form like this. Okay. For each of these eigenfunctions that correspond to those eigenvalues, there's going to be the fourth root of. It's going to be a little bit involved. But they do have interpretation, okay, and special properties. But we're going to have e to the minus omega x squared, okay, divided by 2h. Should be a 2. Sorry, that's horrible. divided by 2h, okay, times some h sub n. And of course, this is just to ensure orthonormal bases, which we require in the integral or the integration of them. Okay, so we're going to have some kind of function or some kind of expansion of some basis function here with this kind of factor in front, which depends on the on this square root or something scaling the coordinate. Okay, and so what these functions are, or what this h sub in of c is, okay, where c is, let's say this z here, okay, what this is that the ground state function is going to have this special property here, where, so we'll say that the ground state function, where we look at the first basis of this, this has to equal 1, and n has to equal 0, okay, as we required before, okay, so that we can have that special ground state wave function, and of course this will be a Gaussian function. This is going to be, we're going to refer to this as a Hermite polynomial. All right, just to introduce this, okay, this gives us our eigenfunctions that solve the simple harmonic oscillator in the quantum kind of perspective, okay. So and it solves it, accounting for these principles of uncertainty, okay. So that's kind of what I wanted to show you. We will have more practice and understand these Hermite polynomials a little bit more in future episodes, and formally, deconstruct their properties and work out some examples. But Hermite polynomials are inherently what we're going to be associating with simple harmonic oscillators. Okay, so let's find the lower limit of the oscillator energy from uncertainty. Okay, let's find that, because that seems like to be the overall question of why is the 0 point energy showing up. Okay, so let's look at the uncertainty relation that we derived, where we say that the uncertainty in the momentum and the position is bounded, is bounded below by this h bar divided by 2 from from that statistical theorem that we had for self-adjoint operators. Okay, so what we need to do to try to use this relation, okay, we're going to use this relation to estimate the ground state energy of these harmonic oscillator. So use to estimate I guess to estimate E0, okay, of the simple harmonic oscillator, okay, of the show. So the average energy, okay, the average energy is going to be equal to the kinetic energy, of course, plus the average potential energy. Okay, and this is going to be equal to the average momentum over 2m plus, the mass times the omega squared times the average position squared. Okay. The reason why we're using averages in this case is to show this kind of equivalence between the operator theory and our definitions of average, or of average, value, or mean value, expectation value. All of these things kind of have this direct correspondence in quantum mechanics to operators. Okay, so what we can do is say the average momentum and position are 0. Okay, so let's say the average momentum and position are 0. Okay, the variances then, so the variances of so let's say the variances are then going to be equal to the uncertainty squared, okay, and the momentum, the uncertainty of the momentum squared. Okay. And so, oh, and I'm sorry, I didn't write this out. Hopefully that's not confusing. So the momentum squared, the average momentum squared is going to be equal. We're defining this in terms of the variances. Okay. And so what we can then have is that the average energy is going to be, of course, we're substituting in the variances instead. This will be useful because we're setting them equal to 0. And so from the uncertainty principle, we know then that the momentum, the uncertainty of the momentum, must be bounded above by h bar over 2 delta x. Okay. And so since we know this, that's a delta. Sorry. And since we know this, to find the minimum possible energy, we can substitute this minimal value. Okay, so we substitute this in this minimal value to find the average energy that we should expect if our the average position and momentum are 0. Okay, and so this is kind of a weird thing to wrap your brain around, because we typically don't use these statistical definitions for deriving physics, right? This is kind of the first time you really use this in physics. But, okay, so, oh, I'm sorry, I just rewrote, I didn't mean to write that. So what we can then have then is that, if we simplify this out, this must actually be bounded above. The average energy must be bounded or equal to some of the constraints from the uncertainty. Okay, so we have the variance divided by the variance of the position plus 1/2 m omega squared delta x squared. And so we can now find that the value of delta x, or the uncertainty of x, should minimize the expression for the energy. And so let's let f of x, or f of delta x, okay, let's let this be the right hand side. Okay, and so if we were to set its derivative with respect to the uncertainty in x, so if we said df by dx, okay, is equal to the negative, okay, h bar squared, we should get a 4m instead because of the power rule. We're just going to kind of assume you can do that. Plus m omega squared times the uncertainty in x is equal to 0. Okay, if we set this equal to 0, and then if we were to solve, so let's change our page here. But if we were to then solve from the last expression, solve for the variance, which is the square of the uncertainty. Okay, so this would give us m omega x squared equal to h bar 4m. Just trying to rewrite what we got in the last page. Okay, we have this. This would then imply that the square of the variance, or the variance, or the uncertainty to the fourth, would be equal to 4m squared omega squared. Okay, and so this will also then imply that the variance squared should be equal to h bar over m 2m omega. All right. So then what we can do is that if we substitute this value back into the energy expression that we had, this should give us the minimum energy, because we set the function we set the derivative of the function with respect to the uncertainty to be equal to 0. If we set this back down, if we set this into the we can now call this the minimum energy that we should have. This should be equal to the h bar squared over 8m h bar divided by 2m omega plus 1/2 m omega squared times h bar divided by 2m omega. Well, this will then, once you simplify it out, that term should just be h bar omega over 4 plus another h bar omega over 4, and we would then get, of course, our solution for the 0 point energy. This simple estimation shows us from the uncertainty principle how statistically useful, or how it is useful to use statistics in physics, okay? And so this correctly yields the exact ground state energy of a linear one-dimensional harmonic oscillator, okay? So this is a very important kind of concept I think you should really try to understand, and the power of quantum mechanics in this uncertainty relation, and why we now can predict something called a 0 point energy, because we are actually uncertain about our measurement to begin with. And so, for momentum and position to be 0, we can't know that it's 0, which is a very surprising result, okay, for just a simple linear harmonic system. Now let's look at motion in a homogeneous field, okay? So let's look at a homogeneous field. So let's say there's a particle in a uniform field, okay? So let's say that u of x is equal to, I guess, the negative, some negative f times x, okay? So the potential is linear, basically. It's gonna depend linearly on f. Let's look at this. So the Schrodinger equation, we can write it out. Let's write it out here. X squared plus 2m divided by h bar squared e plus fx acting on psi, and this should give us 0. Well, the energy spectrum is continuous, okay? From e to negative infinity to e to positive infinity, because it's always going to be positive, okay? And so by making the substitution, then we can kind of just, all right, let's see, let's call this z, okay? Let's say that this is, I guess, let's say this is x plus, I guess, e over f, okay? Times 2m f divided by h bar squared to the 1/3, okay? The reason I'm going to just make this coordinate here is because we can transform the entirety of this Schrodinger equation here once we substitute in this expression for c as just psi double prime, or the second derivative of z, okay, of this quantity here, plus z of psi to be equal to 0, okay? So if you can substitute that in for yourself if you want to see it, but that's basically what happens to the form. And the solutions that are finite. So for solutions finite for all t are the Airy functions. Okay, we call these the Airy functions. I don't really know why they're called Airy functions, but if we have the psi, or if we have some phi, which is the negative of this, okay, this would be the solution for this, okay, for the Airy functions. And the function will oscillate. So the property of this function is it oscillates for it oscillates. Sorry, I spelled oscillates wrong. You guys know what I'm saying. So it oscillates around this classically allowed region, okay? So this x for x greater than negative e divided by f, okay? So it's greater than this, and decays exponentially, okay? It decays exponentially for the negative values of t, and this would be the classically forbidden region where x is less than the energy divided by that linear factor in the potential. Okay, so this is an interesting kind of problem as well. The Airy functions. Something important to know basically from the Schrodinger equation in one dimension. So we looked at the symmetric potential and then we looked at the linear potential. Okay. Last thing we're going to look is I think that's important to understand about the Schrodinger equation, is this idea of reflection. Okay, so we're gonna call something we're gonna determine some reflection kind of magnitude or reflection coefficient from a particle with energy that is greater than some potential energy, some reference potential energy from a potential wall. Okay, so we have a potential wall, a rectangular potential wall, or we could call this a step potential. Okay, and so what we're going to want to do is basically just set up this potential to be, let's say x, u of x is equal to 0 for x is less than 0, and let's set this up so you can see this, some reference potential energy, the rest, okay, for the rest. So this is just a big wall, if you could think about this. It's just a step. It just, it's 0, and then it just kind of like, it just kind of takes on a value here, and it's just this wall. That's what I mean, okay, for u of x. And this, of course, would be x here. All right. Cool. All right. So for x is less than 0, right? Let's use kind of our conditions for the Schrodinger equation. So for x is less than 0, let's say that psi of x. Let's say that psi of x is equal to. Let's use this Napierian base here for these different coefficients we need to find. But it's going to be the same kind of wave factor here, okay? And this kappa, or sorry, this k1 is going to be the square root of 2m times e divided by h bar. And so this incident amplitude, we're going to set it equal to 1, okay? So this is the incident amplitude. Okay. And we're doing this here so that we can find the reflection amplitude. Okay. So this is for x is less than 0. Let's look at for x is greater than 0. Okay. Let's put these in parentheses. For x is greater than 0, we can say that psi of x is going to equal just some other amplitude, let's say a, with some new kind of coefficient here. For k2 is going to be the square root of 2m e minus the potential here. Remember, that's the energy, the potential energy here, and then of course it's also going to be h bar. Okay, so of course these kappa or these k kind of coefficients need to correspond to the energy levels here. And how we're allowing it to propagate, or how we're allowing it to scale with the time coordinate here, okay, for that part. So, okay, there's really this only transmitted wave here that we're measuring, all right, or some transmission amplitude, okay. So let's call this transmission. So we have some incident amplitude, where we're just going to have it 1, some reflection amplitude, and some transition amplitude. Okay. Of course, we also need to imply this, or we need to effectively assert the conditions for the Schrodinger equation that we talked about earlier, which was that psi and psi prime, or the derivative of prime, at x, at x is equal to 0. Okay, so this is x equals 0. Okay. This initial value for psi of 0 should be 1 plus b is equal to a. All right. And we can also have that psi prime of 0 should have this quantity here. We have ik1 times b is equal to ik2 times a. This just comes from taking the derivative of our bases here, okay, for the psi. Okay, so really both of these wave functions, or basically you can kind of think about the wave function here being a function for different, like for x is greater than 0, and then for x is that, basically, okay. And so we must employ this kind of continuity here with the derivative at that point, okay. And so when we substitute the first kind of equation, we're going to substitute this into this, okay. Let's clear the page. We're going to have k1 times 1 minus b is equal to k2 times 1 plus b. What we can then have here is that k1 minus k1b is equal to k2 plus k2b. Okay, which then let's go run circles. We can then have k1 minus k2 is equal to b times k1 plus k2. Okay, that just kind of this comes from algebraically subbing this in, and then solving for the reflection amplitude that we want. So we got k1 minus k2 is k1 plus k2. Interesting condition. And the reflection coefficient, so the reflection coefficient r would be the squared amplitude of this, okay? It would be the square of the amplitude, or the square of the reflection amplitude, or the squared modulus, okay? Or in this case, they're just real numbers, so it's not really that big of a deal, but we'll get this kind of form here. All right, and okay, but we know what these what these coefficients are. So if we just sub them in from our definitions earlier, we just have this kind of difference in the square root of the energy levels, which is very interesting. All right, and then this is all squared, and so the transmission coefficient, of course, would be equal to 1 minus r, okay? So just 1 minus this. And so note that for E, as this E approaches that actual energy level, K2 goes to 0. And also note that for the squared modulus, or the reflection coefficient, okay, how much that wave is being reflected. Essentially, that's what it means. As it goes to 1, where it's completely reflecting the wave, the energy has to go to infinity, and so K2 goes to K1. And sorry. That's not true. I was reading this wrong. So the energy here, as the energy goes to the as it's equal to the potential energy at that wall, what happens is that the K2 is going to go to 0, and the reflection is going to be reflection coefficient is going to be 1. So the magnitude of that reflection is completely there. Okay. Now, the other condition here, and the last thing that we're gonna notice is that if we say that the energy goes to infinity here, K2 approaches K1, and so there's basically no reflection coefficient. Okay, so hopefully that was clear. I think this was an interesting video. It was a bit long, but I feel like it was necessary because Schrödinger's equation is extremely important to grasp, especially in the special cases that we have in one dimension. So we really wanted to explore that, and next next episode, we're going to talk about angular momentum, and basically derives to more of the necessitated quantum theory, because of course we've talked about conservation and energy and conservation of momentum, but we haven't talked about rotations. So we're going to talk about rotations next time. So thank you guys for watching, and I'll see you all next time.